In this video, we are going to show you how you can run a large language model on just 60% of a single GPU on Kubernetes with the model weights and the server shipped together as one signed reproducible artifact. We'll deploy a Qwen3 4 billion parameter model with a single kubectl apply command, watch it get scheduled on a fractional slice of an NVIDIA A10 GPU, and get live streaming inference out of the other end. We'll use Project HAMi for the GPU virtualization and KitOps for the model packaging. And along the way, we'll explain why would you use KitOps instead of pulling the model directly from Hugging Face and then running the whole thing end to end on a live cluster. So here is the biggest pain. GPUs are expensive and scarce, but most inference workloads, especially for small models like a 4 billion parameter model, does not need a whole GPU. A single A10 has 24 gigs of memory. A 4 billion parameter model with decent quant needs only a fraction of that. So teams end up doing one of these two bad things. Number one is one pod per GPU. So you burn the whole card on a workload that only uses 20% of it. The second one is manual MPS or time slicing hacks. These are usually brittle with no hard isolation, and one noisy tenant could starve the others. Let's talk about the other problem. So the other half of the problem is, how do you ship the model itself? The usual answer is that you pull the model from Hugging Face at container start. Now that's a runtime network call to a public hub with no signing, no versioning, pinning that you can control. And if Hugging Face goes down, your pod would basically never come up. So in order to circumvent some of these problems, let's talk about first Project HAMi, which is the heterogeneous AI computing virtualization middleware. So it's a CNCF sandbox project that's recently got incubated, fully open source. And what exactly does HAMi does in one sentence? So it lets you slice a single physical GPU into fractional virtual GPUs and schedule them on Kubernetes with hard limits on both the memory and the compute. The best way you use it is beautifully simple. So instead of asking for NVIDIA GPU 1, the whole card, you add 2 extra resource limits to your pod spec. The number one is nvidia.com/GPU memory %, which is 60. So you cap the container to 60% of the card's VRAM, and NVIDIA GPU cores 60, which basically caps it to 60% of the compute cores. So what essentially HAMi does, it installs a scheduler and a device plugin. The scheduler places your pod on a node with a free slice, and the device plugin enforces the cap inside the container. Now here's the magic part. When your process runs NVIDIA SMI or asks CUDA how much memory actually exists, HAMi intercepts that and reports the sliced number, which is like, let's say 13.8 gigs and not 24. So the app genuinely believes that it is a smaller GPU. It can't over allocate even if it tries to. And that's the real isolation. And also talking about KitOps, so it's a CNCF sandbox project which helps us to solve the packaging problem. So since we know that KitOps introduces the model kit, which is the standard OCI compliant package that bundles everything that you need for an AI project, all the way from the model weights, the config, tokenizers, datasets, code, and documentation into a single versioned signable artifact. And being OCI compliant basically means that the model kits basically live in the same registries that you already use for container images, and you push and pull it exactly similar to a Docker image. And you define this with the help of the YAML called kit file, which is similar to a Docker file, but specifically for a model artifact. And here you can see a kit file example where we have highlighted model.path, which is the Qwen3, and we have the license as Apache 2. And then we also have Jozu Hub, which is a public registry for built particularly for model kits from the team behind KitOps. And that's where our Qwen3 4 billion parameter model in this particular demo will be stored. Now, there's a part that basically ties together for the demo. So Jozu can also serve a model in two different shapes. The number one is a plain model kit. That's just the data which you pull and serve with your own runtime. The other one is a Jozu runtime inference container, or an RIC. And this is an auto-generated container that has the vLLM server and the weights of the model baked in with an entry point that starts an OpenAI compatible API on port 8000. So you just pull one image, run it. That's what you basically do and how you deploy it. Now, the question is, why not just serve vLLM straight from a Hugging Face repository, right? There are 4 reasons for that. Number one is reproducibility and immutability. Hugging Face repository can change under you. So someone force pushes new weights to main and your same deployment is now different. A model kit is content at rest and it's also immutable. So the digest pins the exact byte. Now, second is that it's also an OCI artifact. So it means that it lives in your registry, next to your container images, behind your own auth. no runtime dependency on a public hub being up, right? Which means that your cluster's image pull path is the only way to reach it. Now, model kits are also signed and their provenance is verified, so you can attest exactly what's there inside of the model kit. This matters enormously for an AI supply chain, which is the newest and the softest attack surface in most organizations. And with one artifact, with the server and the weights, like especially if you're using the rapid inference container, there's no need to download weights at startup. The image is deployable. You just run kubectl apply and the pod is self-contained, which by the way is what makes it survive our demo clusters China region networking. We don't have to worry about that. Now for slide number 7, which is the whole architecture, right? Let's start with number 1, which is the Qwen3 4 million parameter model. This is going to be a model kit living in Jozu Hub, packaged as a rapid inference container. So basically the vLLM plus the weights are signed as one single OCI image. Next is we use kubectl apply for a deployment. So the pod spec sets the scheduler name as HAMi scheduler and those two HAMi limits that we said earlier, which is 60% memory and 60% cores. Now third is that the HAMi scheduler basically finds a GPU slice and places the pod, and the device plugin carves out a 60% fractional vGPU on the actual physical GPU. Finally, before streaming, we have the RIC entry point, which boots vLLM, loads the baked in weights and serves an OpenAI compatible endpoint on port 8000. And finally, we hit a normal chat completions request and get the tokens back. And that's how you basically are able to securely package plus get a GPU virtualization fully reproducible. Now let's take a look at the actual demo and how it performs. So what happens initially is that you connect to the cluster. You basically just run the kubectl get nodes. Then we have step number 2, which is prove that it's actually a Jozu Hub RIC. Then we basically look at step 3, which is proof that HAMi has actually virtualized the GPU. So you basically see that the script basically prints the scheduler's name plus the resource limits and then runs the NVIDIA SMI inside the pod. So here basically, the scheduler name, which is HAMi scheduler, the HAMi's basically placed this particular pod and not the default scheduler. And the limits are basically set as GPU cores as 60 and the GPU memory the GPU memory percentage as 60. So if we basically exec into the pod and run NVIDIA SMI, the same tool would basically run on bare metal. The physical, A100 has 23,000 megabytes of memory, but inside the container, NVIDIA SMI reports only 13,800 megabytes, which is exactly 60%. So the application literally cannot see the rest of the card. And that's HAMi. So one physical GPU sliced into a fractional vGPU with a hard limit. Now, when we take a look at the step 4, so now we have basically an open connection to the server. So here we basically port forward the pod and ask it what model it's serving, and we get the result. Then we have step 5, which is live streaming inference. So here see a normal chat completions request and we can see the Qwen3 model, which is basically running and it's streaming back tokens in real time generated on a GPU that is only 60%, right? Which is fully OpenAI compatible, running on a fraction of that particular card. And the 6th step is where you can see that the request actually hits the RIC. So the script basically tails the pod logs and chat completions API and the 200 OK line that you can see. And here we basically tail the pod's logs and you can see the access line over there. And that's essentially the request, right? Which is served inside the HAMi virtualized pod by using vLLM server that basically came from Jozu Hub. So that's the entire end-to-end demo stepwise that we have basically described. So that's a quick demonstration of what we wanted to show, how you can securely package the model and then also make efficient use of the GPUs with the help of the Project HAMi project that you should go and check out. So if you have any other questions, do check out our Discord as well. Thank you so much.